All right, this lecture is on average atomic mass and how to calculate it. All right, now when we think about isotopes or ions, we know that protons define the element. So for any atom, protons define the element. Remember that isotopes of an element all have the same atomic number, which means that they have the same number of protons, but the number of neutrons is different. And then an ion is basically just an atom that has lost or gained electrons, and those have charges. Isotopes and ions are not connected, therefore something can be an isotope and an ion. It can be both. All right, so this lecture is on the average atomic mass. So this is the number that you see on the periodic table underneath each element. The main thing to remember is that this is a weighted average. It's not just like you take the three numbers, divide it by 3, and then you get your average. It's a little bit different. So the masses of the different isotopes are not considered equally, but rather according to abundance or prevalence on our planet. So when scientists find a certain element, let's say, we'll look at sulfur in just a minute. So when they find sulfur, doesn't always exist in just one form. So there's multiple versions of it, again, those isotopes, and the isotope that's the most prevalent, so like they find in the highest percentage, that one's going to have the largest effect on the mass. And the kind of sulfur that, maybe they find very, very rarely, that one would still contribute to the average, but just not as much. All right, so it's similar to weighting of like tests and quizzes in a class compared to the homework. It just takes up a higher percentage versus, the homework, which is small percentage. All right, so to find the average atomic mass, so the one on the periodic table, we're going to need to know what are the isotopes for the element and how many different isotopes are there. So we need to look at every single possible isotope for that element. We need to know the mass of each isotope, and we're either told the mass number, or if we're not told the really specific mass, we can assume that it's the whole number, and we'll talk about that in a second. And then we also need to know what's that natural abundance of each isotope. So when that specific element is found in nature, what percentage of the time is it this isotope? What percentage of the time is it the other isotope? Or maybe a third isotope? All right, so here's our example with sulfur. It says that sulfur has 4 naturally occurring isotopes. We can see sulfur 32, 95.002% of the time that sulfur is found in nature, it's that sulfur 32. We've got sulfur 33, we have question marks there, so we must not know that abundance, or scientists do, but we don't for this problem. Sulfur 34 is 4.22% of the time that sulfur is found, it's in the sulfur 34 form. And then sulfur 36, 0.014% of the time is sulfur 36. So the natural abundance of the 3 isotopes is listed above. So the first thing that we want to find is how many neutrons does each isotope have? All right, remember, that's what makes an isotope. Same number of protons, but different number of neutrons. So the first thing we'd have to do is take a look at the periodic table and figure out, well, how many protons does sulfur have? All right, so for each one of these, since they're all sulfur, we have I don't want to be in the highlighter. All right, so protons are 16. So sulfur's atomic number 16, remember that's the same thing as the number of protons. Remember, this number that comes after the dash is the mass number. So that's protons plus neutrons. If we take those numbers and subtract 16, that's going to tell us the number of neutrons in each one of these guys. All right, so I'm just going to go ahead for the first one. 32 minus 16, it looks like my number of neutrons is going to be 16. For sulfur 33, looks like my number of neutrons is going to be 17. Sulfur 34, 34 minus 16, 18. And then the last one, sulfur 36, 36 minus 16, that's 20. All right, so we answered the first question. Now the second question. What's the natural abundance of the sulfur 33 isotope? All right, well, since these are all percentages, we know that all percentages add up to 100. So what I'm going to do is add up sulfur 32's 95.02. I'll add up this 4.22 and the 0.014 from sulfur 36. All right, so I'll do that off to the side here. I'm going to zoom in. Oops, I need to see the percentages. All right, so I'll have 95.002, 4.22, and 0.014. I'm going to add these guys up. 99.236%. All right, so that's what all of the other isotopes together are. Since I'm looking for this missing one, all I'm going to do is take 100, because I know that all percents add up to 100, minus this 99.236. So whatever's left over must be sulfur 33. And I end up getting 0.764% is sulfur 33. All right. Now, on this next slide, it's just an example. Again, this is showing you sulfur. We can see that we have sulfur 32. Those guys would be purple. Sulfur 33. These guys are green. Sulfur 34, red. And then sulfur 36, blue. Which for some reason they're not really showing up here very well. But if you take a look at the sample, it just shows you all the different atoms of sulfur. Again, this is like what scientists would be able to like distinguish. So they'd see a sample of sulfur, and then they'd be able to, figure out that there's different masses within that sample. All right, so again, isotopes. So the average atomic mass takes all of these percentages or all of the amounts of each one of these isotopes into consideration. So it's a weighted average. All right, well, due to the weighting, the atomic mass that you read in the periodic table will most likely reflect the most abundant isotopes. So it's only going to be obvious to tell which isotope is most abundant only if it's far more abundant than all the others. Okay, so here's some examples. So most elements have 2 or maybe even more isotopes that contribute to the average atomic mass of that element. All right, so the first one listed there is lithium. It has 2 isotopes, lithium-6 and lithium-7. Okay, and we can see that right here. We've got our mass numbers. And the average atomic mass, so the weighted average mass, is 6.941. All right, well, if you take a look, that's closer to 7 than it is to 6, right? 6.941. That's pretty close to 7. All right, so the most prevalent isotope is lithium-7. So we could have predicted that just based off of the number that we see on the periodic table, because it's closer to one of the isotopes versus the other one. So lithium-7 must be really, really prevalent, must have a high percent abundance. If we take a look at carbon, we have carbon-12, 13, and 14. But the average or the weighted atomic mass is 12.01. All right, well, just based off of that, we can predict that carbon-12 is the most prevalent, which it is. We can see that here. All right, so we have oxygen, oxygen 16, 17, 18, but the mass on the periodic table is 16, or like really close to it. I think on our tables it's like 15.999. So 16. That means that oxygen 16 is the most common isotope. All right, we've got fluorine. If you take a look here, there's only one isotope. just one version of fluorine, which is why its mass is a nice whole number on the periodic table. If you look at sulfur, we just looked at that one on the previous slides. Sulfur 32, 33, 34, 36, but the average atomic mass is closest to 32, and it turns out that it is the most prevalent isotope. And then copper 63, copper 65, mass on the periodic table is 63.55, so we can predict, and it's true, that copper 63 is the most common isotope. All right, so now let's say that we're going to be calculating average atomic mass. If your data is not already in a table, make one. If you have any missing abundances, you want to do that first. Remember, all percents add up to 100, so you can always find a missing abundance. The next thing we're going to do is we're going to take the abundance as a percentage, and we're going to convert it into a decimal by moving the decimal point 2 places to the left. All right, so basically we're just dividing it by 100. We're taking it out of the percent form. So an example here would be, let's say that my percentage was, I'm totally making this number up, so, let's say that my percent was like 78.95%. When I'm converting this into a decimal, I'm just dividing by 100. So decimal place just goes 2 to the right, 1, 2. A new number then, or the number I'd use to multiply, would be 0.7895. So you're just moving the decimal over. Then you're going to take this abundance in the decimal form, and you're going to multiply it by the mass of each isotope. And then you're going to do this for as many isotopes as they're listed. Sometimes there's only 2 isotopes. Sometimes it can go up to like 5 or 6 isotopes. Whatever you're given, just make sure that you include all of the isotopes that are there. Then at the very end, you're going to add up all of the values, and you're going to report this as your average atomic mass in units of AMU. So AMU stands for atomic mass units. All right, so you may have noticed that on the periodic table, you'll see, let's say for carbon, that the mass is 12.01 grams. Remember that amount. If you have one atom of carbon, there's no way it's going to have a mass of 12.01 grams. So sometimes we use atomic mass units instead, just to show that, hey, we know that this isn't going to be the mass of one atom in grams. So atomic mass units. All right, so here's our first example. We have an element that has 2 naturally occurring isotopes. One isotope has a mass of 10.012 AMU and a natural abundance of 19.91. All right, well, I'm going to highlight those in one color because I know that this mass and this percent abundance go together. Then it says the other isotope, okay, so I'm just going to switch colors to make it easier for me to see. The other isotope has a mass of 11.009. What's the average atomic mass and the identity of this element? All right, well, the first thing I'm noticing is that I have 2 masses, but only 1%. We can't find the missing percent abundance, remember, by subtracting from 100. So this the isotope with a mass of 11.009, I can find its abundance by doing 100 minus 19.91. All right, minus 19.91. I end up with 80.09%. All right, so I'm going to highlight that orange because that's the same one that has the mass of 11.009. Okay, well, now I can set up my my calculation. I like to put each isotope in a different set of parentheses. So parenthesis, all right, I'll do the blue isotope first. So I take my mass, 10.012 AMU, times the percent abundance. But remember, we're supposed to take it out of the percent form. So I'm just going to come closer and move that decimal over 2 points. While I'm at it, I'm just going to do it for my other percent as well. All right, so take my mass, multiply that by 0.9. 1991. Close my set of parentheses because that's the end of that isotope. I have its mass, I have its percent abundance in decimal form. And now I'm going to add the other isotope. All right, so the isotope's mass is 11.009. And I'm going to multiply it by its percent abundance out of percent form, which is 0.8009, and close my parenthesis. Now, if there was another isotope, then I would add it similar to like what I did over here. I'd hit like I'd write plus, and then I'd have my other isotope information. But in this case, in this problem, there were only 2 isotopes, so I'm just going to leave it the way it is. I'm going to type this into my calculator exactly the way I have it written here. So I'm going to type in parenthesis 10.012 times 0.1991, close my parenthesis, plus, start a new parenthesis, 11.009 times 0.8009, close my parenthesis, and then I get a super long number. So the number I get 10.8104, blah, 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 bunch of other numbers. I guess the rule of thumb, we're not really going to worry about sig figs when we do average atomic mass calculations. Just take your final number and round it to 2 decimal places. All right, so here we have our 2 decimal places. 0 does nothing for rounding, so that's going to be my final answer. 10.81, and then since we found average atomic mass, don't forget those new units. Atomic mass units. All right, so there's our answer. There's our average atomic mass for this element. The other question that this is asking is for us to figure out the identity of this element. Basically, what we need to do is just go to the periodic table, take a look at the average atomic masses of elements, and find whichever one is 10.81 or really close to 10.81. Remember, sometimes periodic tables have different masses because they have, they may have calculated something in a different way, or they've got their data from a different place, but typically the masses are very close to each other. All right, so if we kind of do a scan for a mass of 10.81, you should see that boron has that mass as well. So this must be boron. It looks like I wrote boron. No. Boron. All right, so here we have an example for magnesium. It tells us that there's 3 naturally occurring isotopes, and we can kind of see those at the top. We've got magnesium 24, 25, and 26, and I could see it in this isotope notation up here. It says to use the information in the table above to calculate the average atomic mass of magnesium. All right, so now, whenever we're doing an average atomic mass calculation, you can use that whole number to calculate the mass if they don't give you a more specific mass. However, if I take a look at the table here, they do give us a more specific mass for each one of these guys. So that's what I'm going to use. If that's not given, then feel free to use the whole number, which would be like 24, 25, 26. But since we have specific ones, we're going to use those as our masses. And I can see right below that, we have our percent abundances as well. All right, so I can take a look at those. Okay, maybe just before I even do my math, I'm just going to go ahead and move my decimal 2 spots for each one of those. Oops. And this one. All right, so then I remember I don't have to worry about moving my decimal during the calculation. All right, so we have 3 isotopes. That means that I should have 3 sets of parentheses. So my first one, parenthesis. I'll take my mass, 23.99. I'm going to multiply that by 0.7870. Close my parenthesis, plus start a new one. All right, see my second isotope, mass of 24.99. Multiply that by 0.1013. Close my parenthesis, plus, all right, and the last guy is over here, 25.98 times 0.1117. All right, so we can type that in exactly like that into our calculators. 7870 plus 24.99 times 0.1013. And last one. So the nice thing about doing problems like this is that after you do your work, we know that this element is magnesium, and we can like go check out the mass on the table and just make sure that we're close. So when I actually add all these guys up, I get 24.3135, again, a few other numbers. I'm just going to round to 2 past the decimal, 24.31 AMU. So then I could find magnesium on the periodic table and just make sure again that this mass is pretty close to the one listed on the table, which it is. And here's our example picture for magnesium and its different isotopes. They're listed down here, again, 24, 25, and 26, with the different abundances. And we can see that the average atomic mass, I'm looking down here, is really close to what I just calculated. So 24.30, if I rounded that to 2 decimal places, it actually would be 0.31. So great. All right, so we have one last problem where you're calculating the average atomic mass of titanium. I'm not going to go ahead and do this one with you, but there's a few things that I want you to be careful with. I want you to try it on your own. I am going to write the answer down so you have it, and then you can check your work. The first thing that you should notice is that there are 5 isotopes. So titanium 46, 47, 48, 49, and 50. All right, so that means that when you write this out, you should have 5 sets of parentheses. The other thing you should notice is that, yes, we have whole numbers here. However, we do have more specific masses. So these guys, the ones on the right, are what you should be using, not the whole number masses. All right, so use the highlighted masses. I'll take those away. All right, and the other really common mistake that people make. All right, let's take a look at our percentages. So we're used to seeing numbers like the third one down, 73.40, so like double-digit percentages out front. So then when we move our decimal, we end up with 0.7340, which is fine. But be careful with percentages that don't have double digits, like literally all of the other ones in this problem. So let's take a look at the first one, 8%. So you still want to divide that by 100, take it out of decimal form, 1, 2. So the number that you should be plugging into your calculator will be 0.0800 times 45.953. All right, same thing with this number, 0.07, 0.05, 0.05. All right, so be careful when you plug all of those in or when you write them out, because those are really common mistakes. People will see a percent and they'll just put 0.530, but it's not the same thing. So just be careful. Still remember to move the decimal place twice. All right, so go ahead and try this. I'm going to put the final answer down here, round it to 2 decimal places. I got 47.87 AMU. All right, so please try that. Make sure you get that answer.